And I did like post the last session on my website. It's this one, Fun with ASTs. So if you want to rewatch that one, you can. It's even have a transcript and everything. But I'll give you a brief recap of what we did last time. So basically, I have this very simple JavaScript program, and what we're trying to do is we're trying to find all the unused variables in the program. So like this B variable, that's unused because we declared it, but then we did not reference it later in the program. So we're trying to write a program that can read this code and figure out, oh, B was unused, you don't need it, and then tell you about that. So the step one is to parse this code, and luckily there are off-the-shelf open source JavaScript parsers that we can use. We use one called sprima, and we just said sprima.parse, give it the code as a string, and out it gives us an AST structure. We save that AST structure into a file like this. So this parse program, the way you use it is like you say node parse JS, and then you give it the path to a JavaScript file that you want it to parse. It parses it and it will spit out a .ast file. So we're looking at this .ast file, and last time we sort of read through the AST structure in some detail. And what we also did last time was we wrote this traverse function which traverses this AST. And we'll run this code right now, show what we have here. So you run this traverse program and you give to it as argument an AST file. And then what it does at this point is it traverses the whole tree, and along the way it prints out the sort of node, or at least some information about the node as it's traversing through each node of the tree, and in an indented fashion. So that's what this code does. There's like 60 lines of this. So we're almost there to solving the problem. I think we just finished this sort of basic traversal functionality last time. So what we're going to do this time is we're going to use this traverse function to solve our original problem, which is I would like to be able to find all of the unused variables in my program. To do how would we do this, by the way? I want you guys to give me some ideas. Given that we're now able to, convert this code into an AST that represents that code, and now we have a traverse function that can walk every syntax node in the AST. What is the next step we need to do in order to find all the unused variables in this program? Mm-hmm. Yeah. Yeah. So I mean, yes, that's usually a good thing to do because you might want to traverse the tree for different reasons, right? Now could you maybe, for our specific problem though, like the problem being you're saying we need like a generic function, but I also want to get specific. Like for our problem of I want to find unused variables. What are the steps? Like step one is to what? Okay. Yep. Find. Yep. Find all the variable declarations. Right. And then step 2. Yeah. And how would you do that? Yeah. So what happens? Like um. Let me do a split screen here. So like basically we want to find the references to the variables that might be declared, right? Like for example, this is a reference. This A is a reference. So this is statement 1, statement 2. This is statement 3. This statement 3 is like we're declaring C, and the initial value of C is this binary expression, this plus operation in particular, and where the left hand side is this A, and the right hand side is this 1. So I think this identifier A is what you're kind of looking for, right? Mm-hmm. Mm-hmm. Yeah. Like put maybe a dictionary would be more convenient, and stick them and put them into a dictionary. Find all identifiers and remove them from the dictionary. Does that sound right? And then uh oh, so like okay, so there's actually we don't want to count the declaration as a reference, do we? Because if we counted this as a reference, then we would automatically count it as used, even though it hasn't been used. Oh, 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 I see what you're saying. You're saying if it don't, if we count the declarations also as usage reference, then if it only has one usage, then it then that's proof that it was only declared but not used. But I think I have a counterexample to that, because I can say that I never declare, and I think that still parses. Let me see. Yeah, that still parses. But what ended up happening is I actually have a reference to Z, but I never declared Z. The parser doesn't care. When you run it, there's going to be a problem. When you run it, it's actually a runtime exception. It in some programming languages, they will check that in compile time and not even let you run it. But in JavaScript doesn't care. It just tries to run it. When it gets to that line, it's a runtime error. So I think that's a big problem in a long-term sense because, like, John's strategy is I'm gonna, regardless of whether it's a declaration or a reference, I'm gonna count it the same way. But I'm saying that doesn't really work due to this, right? Because if we use John's strategy, that this would count as we referenced it once, and his strategy is if yeah we've mistakenly counted this as a declaration when it's not. Yeah. So I think we actually somehow have to distinguish an identifier that's within a declarator versus an identifier that's not in a declarator, and that's actually make it more hairy, but it's doable. Yep. Yeah. So yeah, that's true. Um, we could either do that, or we could let me think. Uh, yeah, we could either provide a way to find out what your parent is, which is actually not too bad. We can do that. Or another way would be we can we can provide a way for you to override the traversal behavior. Like you can say, hey, if I am at a, or customize the traversal behavior. We could say, hey, if I'm a variable declarator, actually don't want to traverse the identifier through the normal pathway. I'm just gonna say, okay, I'm a variable declarator. I'm declaring this thing. Don't even bother traversing the identifier, and that way it doesn't get to be recognized as a variable reference. So either of those ways works. Um, but yeah, like it might be it might be easier to, like, because both of these steps, both step one and step two, require a full traversal of the tree, and we want to customize the behavior slightly differently for one case versus another. And yeah, we could make a copy of this traversal function. We can make a whole copy of this traversal function and then tweak it for case one and then tweak it for case two. But there's a lot of duplication of code, and it would be nice to use the same traversal logic for both cases. Um, which which way? So which way do you think is better? Like we just allow the code to know about what your parent is. So if we allowed that, that would mean like when the visitor is visiting this identifier, in addition to the current node you're looking at, we also pass in a parent parameter, and then you can ask, hey, is my parent a variable declarator? We can make that happen. Another thing we could do to solve this is we could potentially have the visitor function. Like in either case, we're gonna pass in a visitor function or visit function, and maybe the visit function can say return false, and if the visit function returns false, then I disable the further traversal of the node. I think either way would solve this problem. Which way do you prefer? Got it. Okay. Let's go ahead and do that then. Oh, anyone want to pair with me? Last time we did this like mob programming, like a mob programming thing. Does anyone want to like we can switch back and forth who's driving, that kind of thing? Does anyone want to control my keyboard? Cool. Cool. Maybe we could like switch like after 20 minutes or something like that. But yeah, go ahead. Can you ask to control my screen or something? I don't remember. Oh, okay. Allow. Okay. All right. So the first thing we want to do. I think a good step towards our goal is like currently what we're doing is when we run this traverse file, when we run this traverse script, it goes through and sort of prints out for each node. It prints out the type. We also have a couple of extra print statements over here, like here, here, and here. I'm thinking let's disable these for now, maybe for good. um, and what we're gonna do is we're gonna pass in a visit function and like have the visit function can do this print out if it wants to. How about that? Okay, so Danny, I'm gonna let you drive. So basically, we're gonna introduce a visit parameter to this traverse function. Oh, can you type? Oh, okay. Go ahead. I just switch it to a normal keyboard. Okay. So now that means we're gonna have to. Oh yeah, we're gonna need to supply visit over here, and we'll just steal line 22 and let that be the body of our passed in visit function. Let's say line 22 in like over here. Like we're just gonna have the visit function print out the type. Oh, actually, both 21 and 22. Let's do both 21 and 22 because line 21 is the indentation. So let's keep the indentation. Oh yeah, the shortcuts are not in your favor. All right. Line 12. Oh, okay. I see what you're doing. Oh, does it? Oh, you can't paste, can you? Just say paste, and I'll do it. Um, okay. I think we also want to put in the level as a second parameter, just so that yeah, that way we can calculate the indentation. Okay, I think that works. And then on line 12, we will plug in visit node. Oh, I'll let you do this first. Yeah, let's call visit node. Mm-hmm. And then now the thing we always forget is for all the recursive calls, we also have to pass in this visit function. So like line 31, basically any call to traverse, we want to double check that we're passing in visit. Oops. Yeah, that was a lot of code. All right. Let's try this. Let's try this. See if that worked. Looks good to me. I mean, it didn't break. It didn't give me an error or anything, and it still prints this nice coastline looking kind of thing. Okay, so I think. Oh, one more thing is we said if the visit function returns false, then we want to disable the recursive traversal under that node. So let's make that happen first. Oh yeah, put it inside the paren. Yep. Okay, so given this, actually let's run this first. That worked. Let's change this to false. Oh, what? Need a parenthesis here. Okay. Retry this. Okay, so if it's true, it'll traverse. If it's false, it will not traverse. Maybe we try if node type is if its node type is not a variable declarator. Then we want to traverse maybe, but otherwise we don't want to traverse. Does that work? I think it worked. Yeah, I think it worked. For the variable declarators, it kind of stopped. Yeah, but for the expression statement, for the expression statements in this program, they are console.logs. So, and that went all the way through. Yeah, there's co-expression. That's the member expression, and then we have the literal here. These are the arguments to the console.log. So I think that worked. Nice. Very cool. So what this means now is we have this generic traversal function that we could use for both either case step 1 or step 2. So let's do step 1 now. Maybe make a function called find var declarations given an AST, and then we'll just say like it's gonna return. Should we maybe pass in a dictionary? Well, yeah, find variable declaration is vars maybe, and then if we find a variable declaration, we will say like we'll just enter an entry into this dictionary. We'll call it vardict or something. Is that cool? Okay. All right. I'll let you go ahead and drive. If you know what you're doing, I'll let you do it. Oh, let me switch the keyboard back to something you know. I think we want variable declarator, actually, because if you look at the declaration, yeah, the declaration has an array of declarators. Wait a minute, what just happened? Did I expand? Oh, there we go. So the declaration, inside the declaration, there's an array of declarators. So I think you actually want to detect the declarator, and then yeah, and then you'll get access to the identifier inside the declarator, and put that into the dictionary. Wait, no, we don't need. Oh, it won't. Actually, it won't. Actually, it won't unless we return false from our visitor function. So what we could do is, because we just write a custom visitor function just for the task in step 1. And like instead of writing this if statement logic directly inside here, we might write a nested visit function here. And then let's change it back to my keyboard maybe. Okay. Node. So we might want to actually put this logic in here, and then at the end we just traverse the node with our special visit function, and then this top level is 0. And if we did this, then we don't have to worry about the traversal. We can just return true or false depending on we want the traverse function to do the further traversal or not. And that means we actually don't have to worry about the variable declaration, because by default it should traverse down to the variable declarator level. It should traverse as deep as we need it to by default, unless we return false. Yeah, I would probably just like no, I probably just like sorry, I we can just do this. Uh, just verdict, and then we'll make a verdict. So we'll just oh you okay, yeah, it's just communication. Yeah, you didn't see how I was gonna put it together. Yeah, that's what I had in mind. Oh, let me switch back to your keyboard. Okay, so yeah. No, we can assume it must be an identifier. Okay. Oh yeah, this way we can track how many times it's been referenced. Maybe maybe we can like impose a linter rule that says you can only reference it for a maximum of 10 times. um, oh, make sure you return false for the variable declarator case, and that way, yeah, that way it won't traverse the identifiers inside the variable declarator. No, you actually want to return true for the default case, but false only for the variable declarator. Because wait, is well, because there we could have variable declarations inside a variety of things, like inside a function, inside a for loop, inside an if statement. Although we're kind of getting ahead of ourselves. Like for this very simple example, it's probably not a problem. Yeah, we no longer. Yeah. Okay, so now we're probably ready to test this. So maybe after line 14, we can print out the verdict. And then we can test it. Okay, I'll go ahead and run it again. ABC and answer. That looks reasonable. Let me take a look at the. I can't control my cursor. Not sure why. Can you go to click on ex1.js? Okay. Yeah, that looks right. That looks right to me. Those are all the variables that were declared. Nice. So all right. Does anyone else want a turn driving? Anyone? Okay. No, actually no, because the thing we want to count is the number of times it was referred to, but by declaring it, we don't refer to it. Actually, does that make sense? Uh, let's. Oh yeah, he kind of improvised. He deviated from our plan, but that's okay. uh, uh, we could either keep going with the plan, or we could change the plan to uh, and put add an entry. Add an entry. Fine. Uh-huh. Okay. So okay, then I'm gonna change the plan. The plan is now to find all variable declarator and put an entry. Put uh, put an entry into dictionary where the value with value equal to 0, and then find all identifiers um, uh, outside of variable declarators. Actually, there's something nuanced here that we'll need to pay attention to later. So I'll put a star asterisk here and add 1 to the value in the corresponding entry in the dictionary. Does that sound good? Okay. So basically we're gonna make another function very similar to this one, but we're gonna call this find variable references, and we're gonna call it right afterwards. Like we're doing 2 separate passes on the tree, 2 full traversals. Oh, not full, because sometimes we stop the traversal here by returning false, but 2 traversals of the tree. And I guess after the second traversal, we should expect some of the values be non-zero, the ones that did get referenced. Yeah. So if we do it now, that probably won't happen. Yeah. If we do it now, we have 0 values. Now we're going to implement some code here to actually count up those values. Okay. So how should we do it? I'll let John drive here. Oh yeah, let me show the AST here. Yeah, so we're gonna descend down this tree. The function is gonna, the visitor function is gonna visit every node that has a type field. If we choose to return false, then we will stop the algorithm from descending it into its children. So in this case, we're actually looking for identifiers. We're looking for identifiers, but we also want to make sure that it's an identifier that's not directly inside of a variable declarator, because those don't count as references. So that's the trick. So I would say the first thing is to check if the node type is a identifier. Actually, we want one conditional to check if it's an identifier, but a separate conditional to check whether it's a variable declarator, I would think. But we could do one at a time. Like we could do, maybe just do identifier for now. Like just say if it's an identifier, we're gonna grab its name and update the dictionary. And that will be incorrect, but we can still run it and see what it does and see how it's incorrect. Oh yeah. So that would be something like this. This or let's go for this. This A, it's a reference. So that would be statement number 2. No, statement number 3. Statement number 3 over here. So you see this A? This is an identifier, but it's part of a binary expression. Yeah. Oh, you actually don't have to worry about that anymore, because the traverse function has taken care of the traversal. Like we already did that. The giant switch statement thing. We took care. Yeah, it knows which path to go descend depending on what type of node it is. And at this point, like we're at a higher level now when we're writing the visit function, and we no longer have the concern of how to descend down for which type of node. So you just can assume you will get to visit all the nodes by default. Oh yeah. No, that's that. I'll do it. Although this doesn't apply because the node would already be the identifier in this case, so it would actually just be node.name. Okay, go ahead. And so now with the name, yeah, we can go access or change, I should say, the entry in the dictionary now. Would it just be plus plus? Yeah, that is a possibility that it, for example, with the z variable, which was never declared, then it will not have been defined. So I think what we would end up doing is putting a not a number in the dictionary. If uh, yeah, key in is better because the way you've done it would think a zero value was falsy. Name in, yeah. If yeah. I guess if it's not in the dictionary, do we even care? We don't care for this case. For this case, we don't. We would care if we were solving, like, find all the referenced but non-existent variables. But in our case, we don't care. Okay, I think we can run this and see what it does. 2122. So that's more or less what we expected, I think. So 2. So for A, like, because this counts at the moment. So we have 1 and 2 for A. B only has 1 because it's of its declaration. We're counting the declaration for now. And then C has 1 and 2, and answer has 1 and 2. So that seems to be right. So now we need to change it so that we don't count the declaration. So how can we do that? Anyone? Anyone? Like, what's? Mm-hmm. Uh, oh yeah. Let me restate the problem. So we're at step number 2 here. Step number 2 is I want to find all of the identifiers that are outside of variable declarators. Basically, this is more technical speak, but essentially I'm trying to find all variable references, like of this form, this kind. I'm referencing C, I'm trying to find all variable references. But if I only look for identifiers, there's a problem because these are identifiers too. And this is a declaration, not a reference. So I don't want to count this A because this A is inside of a declaration. I don't want to count this one. I want to count this one because that's actually a variable reference. So I need somehow to distinguish between an A that's inside a variable declaration versus an A that is just a reference but not inside of a variable. Well, this is still inside of a variable declaration note, but it's just on the right hand side of the declaration. So I still want to count this one, but I don't want to count this one. So that's also a nuance. Yes, it's slightly it's even more tricky than I thought, but it's still doable. So but the upshot of it is we should write another if statement here, like maybe an else if here. I should write another if statement that says if it's a variable declarator, then we need to do something special. But how should we handle it? So one thing is if you look at the AST, like one thought would be like if we're in here, for example, if we're just look at this simple one first before we worry about this more complex one. This simple one, so that's statement number one over here. You can say, hey, if I'm visiting a variable declarator, then I do not want the traversal. I do not want to visit the identifier node that's inside of myself anymore, because I don't want to get that to get counted as a variable reference, right? So I can return false to disable that, right? So that's what we can do. So maybe that's all we do for now. Let's just do that. So let's just say, yeah, else if the node type is a variable declarator, then we're going to return false. Okay, let's see what it does. Okay, so we got 0, 0, 0, and 1. Can anybody explain why we see this? The 1 is actually correct. So we got one of them correct. Like the answer, we do have exactly one reference to the answer. But what about the zeros? Like, why is it that A is not getting counted? Yeah, because it's on the right hand side. We just said don't traverse any child within this statement, and so the right hand side also doesn't get traversed, and here the right hand side also doesn't get traversed, and therefore this A doesn't get counted and this C doesn't count it. The fact that B has 0 is actually correct, so that's the only one that's correct, but the A and C should have a non-zero value. So any ideas on how to solve this? Basically, this returning false might have been too heavy-handed. So yeah, statement. Well, no. C. Yeah, this is the third statement. This is the one we want to look at. That looks like this here. So this one, basically, we don't want it to traverse the identifier, but we still want it to traverse the initial value. That's basically what it comes down to. So this return false says disable traversal for all of it, but we want to disable traversal for this one, but not disable it for this one is what we need. And Can you think of a way to allow that? Uh, no, it's still not breadth first. It's still not breadth first. Breadth first would be, in order to do breadth first, it would be like, hey, I see that I have a declaration. That's fine, but I'm not gonna drill into the children yet. And I see I have another declaration, but I'm not gonna drill into children yet. I go through everything without looking at the children, and all the way until the end. And then when I'm done with everything, then now I go back to, okay, let me look at the first child of that first thing that I did. And then now let me look at the second child of the first thing that I did. And that's how breadth first search works. But this is not doing it that way. This is still depth first. It's just that we're sort of customizing at which points do we stop traversing, stop going deeper. That's what we're trying to do. Oops. Oh, you're saying like add another parameter. It would be nice if we could add another parameter to the visit function and say, um, that would work, but then we're gonna need to change the contract between our traverse library and our consumer of the traverse library, and and also the problem is for each situation we might need a different set of parameters. Maybe we like pass in a context object or something, and then you can add anything you want to the context object. That's possible, but I don't know. There's a way to do it right now without making a change to the traverse protocol. Can anyone think of a way? Okay. Yeah. Mm-hmm. Uh huh. Yeah. Yes. Yes. Exactly. So this is like it's very nuanced what you're doing here, but basically it's like, hey, disable the traversal of my children, but actually I want to still traverse that child, just not that one. So in order to also traverse that child, I'm gonna manually gonna initiate another traversal, just for that child. So so basically, what that looks like is, and I know it might seem strange that that we're calling the outer traverse function again on the inside, but this is fine. Uh huh. Yeah, and I mean this does show that, this returning the false true false flag isn't all powerful. Like there's limitations what you can do by returning this flag. And this is not super pretty, I would say. Like maybe in terms of API design, this might not be necessarily the best way to design it, but there's a way for us to do what we need still, using just this very simple API design. So I think is still good. It is a slightly counterintuitive. I would grant that, but basically here, yeah, we're gonna we're gonna we're gonna tell the top level traversal function, hey, don't drill into these, but I'm gonna start a new top level traversal function just to drill into this one, and that should solve our problem, I think. Yeah, I think that's correct now. So A was referenced exactly once. B was referenced 0 times. That's the unused variable. C was referenced exactly once, and answer was referenced exactly once. Nice. So now all we have to do is I'm gonna write like for let name in var dict if var dict is 0, I'll print is unused. B is unused. Nice. Nice. I think we did it. We could do maybe I've changed that C to a B, and now it's gonna. Oh, I need to reparse it. Reparse it, and now it says C. C is the one that's unused. Yeah, so this works. Very cool. Very cool. We did it. As you can imagine, well, so I would say like if you followed us this far, you basically got a peek inside of how a linter works, and you can imagine doing this kind of thing for other things you might want to detect. Like I want to detect that I'm referencing a variable that doesn't even exist, or maybe they're expecting this to be a global variable, like they're doing window dot blah, and then I did you didn't declare window in here. Are you expecting it to be a global variable? And yeah, there are well-known global variables. Maybe in your linter you have a registry of the well-known global variables and you test them against that. I don't know. You can do a variety of things and do things like, hey, I want to detect, you probably shouldn't have assignments. Oh, while you probably shouldn't have assignments inside a conditional. That is either a mistake or it might be error prone. Maybe that's one of the linter rules that you want to enforce. You can write a little script like this to detect those things. And if you want to go next level, you can even write code that can automatically fix up the source code. If you want to see, I haven't covered how to do it yet, and if there's interest, I can show you that as well. But you could say, hey, this variable is unused. I'm just gonna automatically delete it from the source code or something. Or if there's like some syntax form that you can detect that you know how to fix the problem, you can just write the code that automatically fixes the source code. Yeah, we're at 3 o'clock now, so this is a good time to stop unless anyone has any questions for me or comments.